In this third part of this video series, we will look at a third application of RedScreen's off-grid battery storage model. Here we'll be looking at village electrification in Zambia, and we'll start out by setting up the analysis. So the idea here is we work for a utility that needs to provide power to a village in Zambia, Africa. The location is going to be 45 kilometers northeast of Mumbwa, Zambia, and I should tell you that I've made up this location. I don't know that there's a village there that needs electricity. I've just picked a location on a map. I'm also making some broad assumptions about the costs of providing power to this village. So it's a hypothetical example. The AC electricity requirement for this village is 600 kilowatt hours per day. It has a peak load of 150 kilowatts AC. And we want to compare using photovoltaics with battery and genset to grid extension. So extending the existing grid so that it reaches this currently off-grid village, and then we can supply electricity from the grid. We are going to look at this from the utility's perspective. That is, they've been charged with providing power to the village, and now they have to find the best option for doing that. In the proposed case, we have the system on the left here. So you can see there's a solar system which generates DC electricity. It's put through a photovoltaic inverter as in an on-grid system that generates AC, and if there is an AC load present, that will be consumed in the load. However, typically there's going to be either a surplus or a deficit of electricity. One option for supplying the electricity is to draw power from a battery pack, and the battery pack provides DC electricity, so we need to put that through a bidirectional inverter which can convert this DC to AC such that it can supply the load. There may be times when the solar system does not generate enough electricity to satisfy the load and to keep the battery pack charged over a period of days, and the battery pack runs down. In that case, we can supply both the load and the charging current to the battery using a genset. That is a diesel-fired engine driving an electrical generator. So that's the proposed case system on the left. The base case that we're comparing it to is grid extension, as we mentioned. So the left is called an AC coupled PV genset battery system. The PV genset battery is clear. That's coming from the photovoltaics here, the battery here, and the genset here. The AC coupling refers to this bus being AC here. That is the solar system. All the DC output is converted to AC, and then the common point of interconnection is an AC connection between the load, the genset, and the battery. So the first part of this will be to configure our analysis. So you will launch a blank RedScreen feasibility study, then we'll change settings as necessary. One thing you should look at, there may be others, is to change the currency to the Zambian kwacha. And in order for RedScreen's suggestions for costs to make sense, it needs to convert from Canadian dollars to Zambian kwacha, so you should assume 1 Zambian kwacha is a little over 5 cents Canadian. You'll have to pick a location for the project, 45 kilometers northeast of Mumbwa, Zambia, and you'll have to configure the facility page. Now I'm going to pause the video here and give you an opportunity to do that. If you have a subscription to RedScreen, you should try this. If you don't, however, unfortunately you will not be able to use the off-grid battery model in RedScreen without a subscription, so you won't be able to do this. But you can certainly just look forward in this video to see a demonstration of how you can use RedScreen for this type of system. So here's how I would proceed. First, I'm going to launch a blank feasibility study by clicking here, as we did before. And before I go into the location, I'm going to go back to File and Settings here, and I am going to, for just this current analysis, change the currency to the kwacha. So I'll look to the bottom of the list, find Zambia, and it selects the Zambian kwacha. I'm also going to change the heating value reference here. As was mentioned in the last video, outside of North America, it's common to use the lower heating value reference to determine the quantity of energy that's available in a unit of a fossil fuel. So we are going to go with the convention that's used in most parts of the world outside of North America. And the other thing I'm going to do just for the current analysis is enter the exchange rate. And we said we were going to assume that 0.53 Canadian dollars is equal to 1 Zambian kwacha, and that is the exchange rate at the time of this recording. Now we go back to the location page here and we select the climate data location. In the search box here, I will search for Mumbwa, Zambia. Double clicking on that takes me to the city here. I'm going to zoom out a bit so that I can move the facility thumbtack 45 kilometers to the northeast. And how can I tell that it's 45? By looking here. It's the distance between the climate data location and the facility thumbtack is 45 kilometers, and that's roughly northeast. So for the purposes of this case study, that's sufficient. I click paste data here and I've got the location entered here, and this gives me the climate data for this site. A few things to note: we're in the southern hemisphere. The facility location is 15 degrees south of the equator. Another thing to note is because we're so close to the equator, the daily solar radiation on the horizontal, there is variability from one season to the next, but it's not as severe as in more high latitude locations such as Canada or Europe or United States. The temperature is somewhat steady. That's this green line. This is the average daily temperature. It ranges between the high teens and the high 20s depending on the time of the year. So going to the facility page, we need to configure this to do a feasibility analysis. We have feasibility selected here, so that's good. It's not a power plant, however. In RETScreen's breakdown of project types, this is a power storage off-grid system, but it is, as indicated here, a photovoltaic system, so we'll leave that. You could fill out all these other cells here. I'm just going to skip that. You could change the image. I'm going to skip that as well, and I'm going to ignore the benchmark by hiding it here. So having done that, the next section we will specify the load and the base case power system.